The goals of Chapter 2 will be, 1, to know the arrangement of the periodic table, that is, groups, periods, what is the alkali metals, alkaline earth metals, halogens, the charges of particular groups. That's the type of level of detail we want to have or know for point number 1. Point number 2, know the structure of the atom. Basically, protons and neutrons comprise the nucleus at the center of the atom, and electrons circulate around them in orbits, also known as orbitals, as we'll find out later on in the course. So protons, neutrons, and electrons, and also how they're arranged, as I spoke about it before. The third point is this concept of isotopes. What are isotopes? And be able to, given an atom, determine how many protons, neutrons, and electrons it has. Point number 4 is ions. So ions are positive in charge. They are cations, and anions are negative in charge. So ions is just simply a charged particle. We'll talk a little bit about ions and their relationship to the periodic table. And then finally, nomenclature. Make sure you know your flashcards. Make sure you know the difference between ionic compounds and molecular compounds and how they are named. Also, we're going to touch upon how to name acids as well as hydrates. There is a Excel spreadsheet in one of the labs where you will get tremendous amount of practice doing nomenclature. So let's quickly go over Chapter 2 notes in this lecture recording while I'm away on traveling. Don't forget your homework problems. Do those problems, check your answers, and turn that in for 10 points when they are due according to the syllabus. So one of the things I want to talk about with this chapter is the fact that you're going to really have to know your flashcards. So knowing those, memorizing those as quickly as you can will help you understand one major facet of this chapter, and that is nomenclature. But before we go into that, this chapter begins with studying the periodic table. And the periodic table contains elements. All those 118 or so little boxes are actually elements. And as we know, elements can further be broken down into atoms, and atoms can further be broken down into protons, neutrons, and electrons. So Dalton formulated his theory of the atom in around 1808, and really it was the Russian chemist Mendeleev who organized all of this in what is now called the periodic table. So briefly, elements are particles, and they have unique and distinct properties. And these properties can either be intensive or extensive. So every element that you see in the periodic table has some unique property. And we already discussed a little bit what intensive and extensive properties are. So here is our periodic table. One of the more important things that you should know is, first of all, you don't need to memorize this, but do carry it. So get a handy periodic table. I'll have some available, or you can get one from the web. And this periodic table is incomplete. It has very little information. However, the first thing I do want you to know, and I believe this is kind of important, is that each of these columns is called a group. Okay, so this is group 1, and in some periodic tables it's also called group 1A. This is called group 2, and in some periodic versions it's called group 2A. So here you have the groups dependent on what type of periodic table you are referring to. It will either be the numerals 1, 2, 3, 4, 5 all the way to 18, or it will be demarcated in either groups A or groups B. Another thing that you should know about the periodic table is that it's separated according to metals. So the color distinction is not very great here, but the colors are going to be... First thing you should know about the periodic table is that it consists of columns, and the columns are known as groups. So that's a term that you should know, groups. And the group can be numbered according to group 1, 2, 3, 4, 5, all the way to 18. Or some versions of the periodic table have the A, B type of naming groups. So this can be group 1A or group 1. This would be group 2 or group 2A, again, depending on the periodic table version that you're referring to. So Another thing that you should know about the periodic table is the properties are separated as to whether they're metallic, so the metals, and the color demarcation isn't the greatest here, but metals are kind of this light green, and then nonmetals are bluish, and then we have intermediate elements that have properties that are both metallic and non-metallic, and that's this pinkish sort of purplish color. So it's worth noting some of the properties of metals. Metals are conductors, and metals are generally going to be kind of hard and malleable. Nonmetals tend to be soft. They tend to be non-conductors of electricity. And nonmetals also are your gases for the most part. Nonmetals tend to take electrons, so that's an important point that we'll talk about later. And metals tend to give up electrons. Hydrogen is sort of an outlier, so just know hydrogen is just put here as the beginning, as atomic number 1. I'd also like to take this opportunity to just focus on, and we will talk about this more later, some of the names of the groups. So what you should know is that group 1 is also known as the alkaline metals. Group 2 or group 2A is known as the alkaline earth metals. I'm going to skip over here to group 17 or group 7A, and those are known as the halogens, fluorine, chlorine, bromine, iodine, and this one here, At element, are the halogens. Of course, we know the halogens are probably, we know them mostly by these 4. And then another term for this last group, group 18 or group 8A, helium, neon, argon, krypton, xenon, and radon. These are the noble gases, also known as the inert gases. Another aspect I'd like to mention to you are charges. So when these elements like to form ions, right now all you see here are neutral elements. But if they're going to form charged particles or ions, group 1, group 1A, or otherwise known as the alkaline metals, are going to be +1. Group 2 or group 2A, also known as the alkaline earth metals, are going to be +2. I'll skip over here to group 16 or group 6A. Oxygen, sulfur, and selenium are going to be -2, but be careful because sulfur and selenium can have different charges. Unequivocally and almost universally, the halogens, group 17 or group 7A, will be -1. And then the inert gases, also known as the noble gases, are going to have charge 0. So these will not form ions. Another thing that I want to mention in the periodic table, again, we're glossing over this. We'll go over this in tremendous depth later on in the course, but it's good to get to know some of this now. Let's focus on one of these elements here in the periodic table. Right? So first of all of these are elements, but what you see here are their abbreviations. So I know some of these by heart, not all of them. I know Li is the abbreviation for lithium. Na is the abbreviation for sodium, so there could have a Greek or Latin root. Fe is the abbreviation for iron, and on and on. So don't have to memorize what they are, though some periodic tables will definitely give you the name of the element below the abbreviation. Let's focus on iron here, Fe. That number 26, or the number on top, is known as the atomic number, and it is the number of protons contained in that element. So iron, Fe, is its elemental symbol, has 26 protons. This is invariant. The atomic number is invariant. It does not change for that element. Very important point. So the atomic number is invariant means that iron, Fe, will have 26 protons in its nucleus. It does not change. Why does it not change? Well, what happens if it gains a proton to 27? Well, it's no longer iron, it's element Co, which is cobalt. So you can see here that this top number is invariant for that element, because if you either increase it or decrease it, you get a totally different element. And that means totally different properties, both intensive and extensive. Forgot to mention, just a quick hit, that metalloids are going to have properties that are intermediate between the nonmetals, non-conductors, usually gases, and then they will have properties of that as well as mixed into them properties of the metals, conductors, malleable, sometimes hard, etc. So the metalloids are going to have both ways, both metallic and non-metallic properties. As we continue on, elements are composed of atoms. So let's look at the iron atom. Iron, as we mentioned before, has an atomic number of 26, which means it has 26 protons in its nucleus. Protons are a positively charged subatomic particle, and these are the arrangements. Right? So I have here a little bit of tidbits or extra notes here that you can write down or just know. Elements, again, are composed of atoms, and those atoms have different properties that make up these elements. Right? Compounds and chemical reactions are just sort of add-ons that I put in there. Compounds are when we join these two or more elements together, and a chemical reaction occurs when we react compounds. We also react molecules. Here I tend to use compounds and molecules interchangeably, though technically there is a difference in their definition. But chemical reaction deals with the transformations of these compounds. So we are going very simple with the atom, but as we join atoms together, we increase in complexity in compounds or molecules. And when we react different compounds and different molecules, we transform them, different rearrangements. That is a chemical reaction. All right, here's another arrangement of iron atoms. So iron, as all metals, they're kind of arranged in an array. They're not gases which are spread out or diffuse, or they're not liquids which are kind of intermediary in the way the atoms are arranged. Solids tend to be packed really close together, tend to be very dense, and as stated before, they tend to be very good conductors of electricity, probably because of that stacked arrangement of their atoms. So here's another display of an iron atom. So if we take one of these Fe little balls and try to go into more complexity or go deeper inside that iron atom, you'll see that there's going to be 26 protons, 30 neutrons, and 26 electrons. So this neutrons, the number of neutrons, has to do with isotopes. I'm going to get into that a little bit later. But you notice here 26 protons is equal to the amount of electrons that orbit the nucleus. And that's because the iron you see here is neutral. Do you see any charges here in the iron element or the iron atom? Do you see any pluses or minuses? Well, if you see a plus or a minus, then the number of electrons is going to be different than the number of protons. Since everything in the periodic table, as I scroll up, all these elements of the periodic table are in their neutral form, that is, you don't see any pluses, you don't see any minuses, the number of protons will equal to the number of electrons. So going back to our iron example, iron will have not only 26 protons, its atomic number, which remember is invariant, but it will also have how many electrons? The answer is 26 because it's neutral. All of these elements are neutral. Right? Picking on elemental symbol Al, that's aluminum. Aluminum will have 13 protons and 13 electrons. Right? Like that, on and on. You can pick any random element off the periodic table. I'll pick a non-metal, iodine. That's the symbol is I. Just as a trivia, iodine likes to be diatomic. I2 is its naturally abundant form. Anyways, element I is iodine, 53 protons in its nucleus, and 53 electrons that orbit it. 53 protons, 53 electrons because it's neutral. Halogens tend to be -1. So if iodine gains an electron, which is a negatively charged species, then it will have 54 electrons, still at 53 protons. I remember a little bit earlier I mentioned that 1 or group 1A, like to be plus 1. Well, an electron is a negatively charged subatomic particle. So if an element loses an electron, it loses a minus 1. So let's pick on sodium. Sodium has 11 protons and 11 electrons, but Na plus 1, sodium plus 1, has 11 protons and 10 electrons. All right, like that, we have iron. Okay, the arrangement of iron is going to be different. It's an element in the periodic table, atomic number 26. Compared to gold, this is the symbol for gold, Au, atomic number 79, 79 protons. Neutral gold, no ions, no electrons gained or lost, no charges, so 79 protons, 79 electrons that orbit and circulate around the nucleus. Again, we won't worry about the number of neutrons until later on in this lecture. All right, continuing on, one of the points in the previous page had to do with compounds. So compounds are a combination of elements, and just to get a quick hit on this, okay, you notice you're going to have nice whole numbers, CO2, okay? 2 oxygen atoms with 1 carbon atom, 2 hydrogen atoms with 1 oxygen atom, 2 iron atoms with 3 oxygen atoms. Sulfuric acid, okay, we're going to have to learn acids in this course. You'll do acid-base chemistry and chemistry 2. Okay, 2 hydrogen atoms, 1 sulfur atom, 4 oxygen atoms. Okay, MnO4, 1 manganese atom with 4 oxygen atoms. How do you name these? Okay, you're going to have to learn how to name both ionic compounds and molecular compounds. All right, Dalton's law of multiple proportions. Quickly, can't have fancy decimals or weird numbers. It's either going to be nice, simple whole numbers. Carbon monoxide, CO, carbon dioxide, CO2. Water, H2O. Okay, no decimals in your chemical formula. Dalton's rule number 2, law of conservation of mass. Very easy, very simple, and very to the point. Mass cannot be created nor destroyed. So the mass has to be accounted for. Even if it leaves the air, or leaves the reaction vessel as gas, that has to be accounted for. So everything gets accounted for as stated before, cannot be created or cannot be destroyed. This becomes important when you balance chemical equations, and we'll talk about that in chapter 3. But for now, mass cannot be created nor destroyed. Part 2, the structure of the atom. All right, first of all, a glimpse into electrons, protons, and neutrons. Electrons are going to be symbolized by E minus, E with a minus sign. Protons are going to be symbolized by P plus, P with a plus sign. That E, that minus sign is a superscript. That P and the P plus, that plus sign is a superscript. So E minus, negatively charged electron, orbiting the nucleus, positively charged proton inside the nucleus. Notice the masses, very small, 10 to the minus 28 grams, 10 to the minus 24 grams, and the neutron, 10 to the minus 24 grams, essentially infinitesimal mass. Neutrons are neutral in charge, okay, so that's worth also mentioning. So minus 1 for an electron, E minus, P plus, and neutron housed within the nucleus with the proton is no charge, neutral charge. The different models of the atom, Rutherford made a lot of strides in this. He had the electrons, Rutherford did, this is about the 1900s or so, had the electrons orbiting the nucleus, all right? And the nucleus contains protons and neutrons, so it sort of orbits it. Right? It's a little bit more complicated than that. By the way, this is the helium atom, and if you look up in your periodic table, helium has atomic number 2, so that means 2 protons, and since this is neutral helium, it's going to have 2 electrons. Helium also is an inert gas, so it's not going to form a charge. Group 8, or group 8A in the periodic table. Okay, Rutherford's model of the atom is pretty simplistic. More complex versions of the atom are there. And one of them is that the electrons not only just don't orbit it, they orbit it and they circulate around it in orbitals. This is where you get your s orbital, p orbital, d orbital, f orbital, if you remember from high school chemistry. And not only that, we won't talk about it in this chapter, but electrons are waves and particles together. Shown here is a manifestation of it, the electron as a particle, little spherical particle that's zoom, orbiting around the nucleus, zooming up around the nucleus, but it also has a wavelength and a frequency. So not shown here is the depiction of the electron as a wave, behaving like a wave. So wave-particle duality around the nucleus is going to be important. That's around chapter 7 or so. All right, important feature here, the way we're going to depict some of these elements that you see in the periodic table is the elemental symbol X. A is the mass number, and the atomic number is abbreviated Z. We mentioned that the atomic number is the number of protons in the element, and that is read straight off of the periodic table. Mass number is something we have not talked about, but it is the number of protons and neutrons. Okay, the number of protons and neutrons. Mass number is where we incorporate isotopes. Isotopes are going to be important, but that's the reason why you have mass numbers in some periodic tables that have these very strange decimals, really weird, quirky numbers. That's because of isotopes. There are elements that have different number of neutrons, and we call them isotopes. Right? So the definition of an isotope is an element that has a different number of neutrons. Right? So the mass number is an average of all those abundances for that element. The example is carbon. There's a carbon 12, a carbon 13, and a carbon 14. So the mass number, which is usually the bottom number in the periodic table, if I scroll all the way up, usually the mass number is shown at the bottom. It's not shown here in this periodic table. You only see the atomic number, but usually the mass number is shown at the bottom, and that is a weighted average. So carbon, that number here, which is about 12.01 or 12.02, is a weighted average of carbon 12, which is found in our body, natural abundant carbon, carbon 13, and carbon 14, which is radioactive. So like that, you have different isotopes of carbons. Carbon is not just C, it's C12, C13, C14. All those isotopes have 6 protons, and they have 6 electrons because, again, no charge, no pluses or minuses. What's the difference between carbon 13, 14, and carbon 12? It is the number of neutrons. Shown in this figure are the different isotopes of hydrogen. So hydrogen, look at your periodic table. What is its atomic number? Its atomic number is 1. How many electrons circulate around that hydrogen atom? Okay, no charges, so it's 1. If you see a plus sign or a minus sign, if you see any ions, then you got to worry about electrons. If you don't see any pluses or any minus signs, the number of protons is the same as the number of electrons. Let's look at this here. All right, how many protons and neutrons are shown here? All right, so you still have 1 proton, but now you have 1 neutron as well. All right, how many electrons are circulating around this hydrogen atom? It's still 1. What about this one here? We have 1 proton because the atomic number of protons is invariant. And how many neutrons do we have here? 2. And how many electrons circulate around this hydrogen atom? It's still going to be 1 because, again, you don't see any pluses, you don't see any minuses, no charges. Okay, the number of electrons equates to the number of protons. So what's the difference between these two? All right, the difference is this one has 0 neutrons, this one has 1 neutron, this one has 2 neutrons. These are 3 isotopes of hydrogen. I can give you their name, but you don't really have to know them. This is hydrogen, everyday hydrogen that you probably know. 0 neutrons. This is called deuterium. Okay, deuterium. Again, don't need to know that. And it has 1 neutron. 2 minus 1 is going to be 1 neutron. And this is radioactive tritium. Again, do not need to know that. Radioactive tritium. And 3 minus 1 is going to be 2 neutrons. So that's how you get the number of neutrons in this configuration. Again, the bottom number, the bottom subscript, is the atomic number. The top superscript is the mass number, number of protons plus number of neutrons. All right, let's take a look at some practice problems here. Number of protons, neutrons, and electrons in the following. All right, so how many protons are here in this sodium element, or sodium atom? It's going to be 11 protons. And how many electrons are going to be in this sodium atom? And finally, how many neutrons? It's going to be 20 minus 11. It's going to be 9 neutrons. Get into the habit of writing E as E minus like this. It's going to be important for later parts of the course, especially in Chem 2. So an electron we symbolize as an E with a minus superscript. A proton we symbolize as a P with a plus superscript. So 11 electrons, 11 protons, and 9 neutrons. Let's do part B. How many protons are going to be in the sodium element? Okay, still 11. How many electrons in the sodium atom or sodium element? 11. How many neutrons? 11. Okay, so here we have isotopes. 9 neutrons, 11 neutrons. Elements that differ in the number of neutrons is the prototypical definition of an isotope. What happens if I put a plus here in sodium plus? Okay. What happens if I make this Na plus? What happens if I switch or modify part B so that it's exactly the same but I add a plus sign? Remember group 1A, sodium is in group 1 or 1A. They like to be plus 1 ions or plus 1 charged particles. And so this is a sodium atom with a charge of plus 1. How many protons, neutrons, and electrons will it have? Right, so it's going to still have 11 protons. Remember, the atomic number stays the same. How many electrons will it have? Okay, look at that plus symbol. So Na plus. All right, so instead of 11 electrons, it has gave up 1 E minus in order to become Na plus. Because it's given up 1 E minus to become Na plus, this actually has 10 electrons. And finally, how many neutrons does it have? 22 minus 11 is going to be 11 neutrons. Okay? So these are not isotopes. Na and Na plus, with 22 and 11, are not isotopes. Remember, this is the bottom number is your atomic number, the top number is the mass number. These two here, 2211 Na and 2211 Na plus, are not isotopes because they all have 11 neutrons. However, the ion form has 1 less electron. So here's sodium and here's sodium ion. What if this lost 2 electrons? It would be 9 electrons if it lost 2 E minus. If it lost 3 electrons, it will be 9 electrons. So like that. Remember, metals lose electrons, nonmetals gain electrons. All right, how about O17? Well, look at your periodic table to see what is the atomic number of oxygen. I don't know it off the top of my head, so I'm going to scroll back up. The atomic number of oxygen is 8. So this has 8 protons. I'll just write it like this. 8 protons. How many electrons? Do you see a charge here? No charge, so 8 electrons. And finally, how many neutrons? 17 minus 8. There actually should be an 8 written in here. So some textbooks like to confuse people and just show the mass number. All right, so that configuration is also legit. But the mass number here is very easily obtained from the periodic table. So this version and this version many chemistry textbooks use. Part C is just to confuse a student, really. Okay, so 8 protons, 8 electrons. What is the number of neutrons? 17 minus 8, it should be 9 neutrons. Right? Carbon 14, one of the isotopes. And what is the atomic number of carbon? I don't know. Let me look that back up here in the periodic table. Carbon should be 6, right? Carbon is 6, so that represents the number of protons, 6 protons. Go back, Danny. All right, 6 protons. And how many electrons? It's still going to be 6. And number of neutrons, 14 minus 6 is going to be. What happens if I change part C from 17O to 17O minus 2? Remember, group 6 or group 6A like to be minus 2. So what does that mean? Right? So O minus 2, everything else being the same, we'll have 8 protons, 9 neutrons, but how many electrons? All right, how did O become O minus 2? It gained 2E minus. So when it gains 2E minus, it becomes 10 electrons. The only difference between 17O and 17O minus 2 is that the minus 2 version is the ion version in which it has gained 2 electrons. All right, what is the atomic number of an element if one of its isotopes has 117 neutrons and a mass number of 195? So 117 neutrons and a mass number of 195. In order to solve this problem, you're going to take the mass number, which is the number of protons and neutrons. So let me write this down, or type this down. So we have a mass number of 195. So 195 equals protons plus the number of neutrons, which was 117. So what's 195 minus 117? It's going to be 78. So 195 minus 117, I think in my head I'm getting 78. So 78 is equal to the number of protons. What has 78 protons? Okay, let me go back up to my periodic table here. 78 is PT. And I just happen to know that PT is platinum. Right? So since I've been doing it for a couple of years, I kind of know a lot of these by heart, but some of them I don't know. Like I don't know what this is. I definitely don't know what these bottom guys are. But some of them I do know. Again, get a good periodic table that gives not only the elemental symbols, but the elemental names. One final thing about the periodic table that I think I did not mention is that we have groups that go down, so group 1, group 1A, group 13, or group 3A. Another thing I forgot to mention is that we have a big rectangular block here, okay, from about group 3B to group 1B, or more simply group 3 to group 11. So this little rectangular block are called the transition metals. The transition metals, very important point. And the transition metals are going to have variable charge. That's one point. The second important point about transition metals is that their charge is going to be designated by a Roman numeral. And the third important point about transition metals is that these guys, remember, all metals are going to have a plus because they're going to give away electrons. So all transition metals will have their charges given in Roman numerals, and they're going to be plus charges. Okay, so iron +2 or iron +3. All right, so those are two states of iron. Another one, vanadium, element V, atomic number 23, has charges that go from +3 to +4 to +5, even +6. So recognize that little rectangular box here. 3B to 1B or group 3 to group 11 are the transition metals, and very important that you know that they have variable charges. The second important point is that I talked about going up and down as a group. Going from left to right or across a row is called a period. So this would be period 1, the periodic table, period 2, period 3, the fourth row is period 4, the fifth row is period 5, the sixth row is period 6, and the seventh row is period 7. Right, we briefly mentioned properties of metals and nonmetals. Metals, as stated before, will be conductors. They're going to have charges that are going to be pluses, so +1, +2, +3, or even up to +5. And they're conductors, and they're kind of hard, malleable, kind of dense, so their atoms are arranged in an array. Nonmetals are non-conductors and kind of soft. If you're going to have some properties, they may be brittle, but most of these are gases. And nonmetals gain electrons. So while metals give up electrons, nonmetals gain electrons. Metals are givers, nonmetals are takers, and periodic table, one of the most primary demarcations of the periodic tables is the metals versus nonmetals characteristic. Of course, we have the metalloids, which are kind of stuck in that diagonal in the middle. All right, now we're entering into a phase of nomenclature. So get those flashcards ready and get those flashcards memorized as best as you can. A couple of terminologies. I talked to you about compounds. There's another term called molecules. And molecules are two atoms in a definite arrangement held together by chemical bonds. So usually a molecule is held together by either an ionic or covalent bond, but they're usually kind of the same element. So O2, Cl2, Br2, N2, these diatoms tend to be molecules. These heteroatoms tend to be compounds. We all group these as compounds, but molecules that are sort of homoatoms or diatoms or triatomic tend to be called molecules. Now, I'm not really going to harp on this because, studying this and teaching this for a couple of years now, I get into that habit of saying a molecule is a compound or a compound is a molecule. So for now, I'm not going to really harp on this point. My opinion, as you grow more and more into chemistry and more specialized, these little nuances are not really worth sweating over. But anyways, I'm going to say most of these are compounds. I'm going to refer to them as compounds. If I say them as a molecule, just realize I'm pretty much saying the same thing. We have polyatomic molecules, so higher levels of chemistry, such as glucose, the main metabolic carbohydrate in the cell or the body, has 6 elements of carbon, or 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. These are all held together by covalent bonds. Acetylene, C2, 2 atoms of carbon, 4 atoms of hydrogen. These are held together by covalent bonds. Covalent means there's actually a sharing of electrons. Carbon dioxide, 1 atom of carbon bound to 2 atoms of oxygen. Those are held together by covalent bonds, sharing of an electron. Now, why are all of these covalent compounds? Well, they are nonmetals joined to nonmetals. Carbon is a nonmetal, oxygen is a nonmetal. Check your placement of these elements in the periodic table, and you'll find that all of these, carbon, hydrogen, and oxygen, are nonmetals. So nonmetals can bind to other nonmetals. How do they do that? By sharing electrons. Okay, very important point, sharing electrons. Now, can a metal bind to another metal? Probably not. Those are called alloys, but that's a different configuration, and we won't be talking about that as much. But we're going to be talking a lot about covalent compounds such as these. A metal that's joined to a nonmetal is an ionic compound. So ions can be positively charged or negatively charged. Positive charge, think of your group 1. Group 2, your transition metals, variable charge. Negative charge, your anions, think of your group 6, think of your group 7, all right? And nitrogen and a couple of those nonmetals are going to have differing negative charges as well. Anions gain electrons, cations lose electrons. All right, so ions are charged particles. Let's beat this point again. So hopefully this should be a review and should be second nature by now. Sodium, right off the periodic table, has 11 protons and 11 electrons. Sodium ion has, by virtue of losing an electron, becomes plus, and it now has one less electron, or 10 electrons. Notice the sodium has this diameter, this atomic size or atomic radii is this version, this size. Na plus is smaller. Why do you think it's smaller? Because it's lost an electron. It's lost that electron. It's lost that electron density. That orbital is no longer housed by an electron. So, yeah, the atomic size is going to be smaller. Okay, conversely, if you take something like Cl or chlorine, looking at it in the periodic table, we find that it has 17 protons and 17 electrons, neutral chlorine. Nonmetals like to gain electrons. Cl minus gains 1 electron, it becomes Cl minus. And when it gains 1 electron, it becomes 18 as the number of electrons the element has. The atomic number, the number of protons, remains invariant. Notice the size of the circle here. Chlorine has this size. Cl minus, is it bigger? Well, it has gained 1 electron. By virtue of gaining an electron, it's gained that electron density, it's gained that wave function, it's gained that particle function. So, yeah, the Cl minus anion is going to be bigger than the neutral Cl atom. The Na plus cation is going to be bigger than the neutral sodium atom. So it may be worth memorizing this table, some of the charges associated with the ionic forms of the elements. Group 1 and Group 2, you're going to just easily know that they're going to be plus 1 and plus 2. Group 6 and Group 7 are going to be minus 2 and minus 1. Carbon is not going to be minus 4 most of the time. Carbon likes to form covalent bonds, so it likes to share. So even though it's minus 4, it likes to make 4 bonds. Carbon is the essence of organic chemistry and biochemistry, so obviously we'll study that if you take that course. Want to bring your attention to this rectangular box here. So through 3B to 1B, actually I misspoke, 3B to 2B, cadmium and mercury, these are the transition metals. Right? These are the transition metal, that little rectangular box, because mercury has, mercury's plus 2, cadmium and zinc are plus 2, so really the transition metals are 3B to 1B, and notice from group 3B to 1B, the transition metals have differing charges, plus 2 or plus 3, plus 2 to plus 1, iron plus 2, iron plus 3, and these charges are designated by Roman numerals. So when we name these compounds with these transition metals, we're going to use Roman numerals. All right, I'll let you do this on your own, protons, neutrons, and electrons for each of these guys, and the answers will be shown below. So when I did this problem set and generated the answers, this is what I got. Just a note on the number of neutrons. What I did was I took the mass number and I rounded it off. So oxygen has a mass number, or that number that's beneath the element in the periodic table. Most periodic tables, the small number or the number with the decimal, it's 15.99. So I just rounded that up to 16. So 16 minus 8 will give it 12. And sodium also is like 22.99 or 22.98 in the periodic table I had. I just rounded it up to 23. And 23 minus 11 is going to be 12. So that's how I figured out the number of neutrons. I just rounded up to the nearest whole number and used rounding rules. So we're going to get to the reason why it's oxygen has a mass number of 16, as a mass number of 15.99 instead of 16. And sodium has a mass number of 22.98 instead of 23. And iodine has a mass number of 126.98 instead of 127. You probably already know the answer, and the answer is isotopes. Okay, the reason why you have those messy decimals in that element for that element has to do with decimals. The fact that low abundance isotopes are contributing to that decimal point, or contributing to that messy number. So you don't have one version of oxygen, O16, but you have O15 that's maybe less than 1%. So that's the reason why you have those decimal places for your mass number, but I just rounded it up to get an easy estimate of the number of neutrons for each of these elements. Actually, elemental ions. Okay, all of these are ions, and oxygen gains 2 electrons to become O minus 2, so it has 10 electrons. And just double check my work to see if I missed anything. So that's how we want you to be able to just quickly, given the ion form of the element or given the neutral form of the element, should be able to quickly determine the number of protons, neutrons, and electrons. By the way, these elements and their ion forms are going to have very different properties. So sodium is very hard, and it reacts very violently with water. It explodes. But Na plus sodium ion is actually an important electrolyte in your body, and it's important for nerve conduction. So you see, just by gaining an electron in chloride versus chlorine, the chloride ion, or losing an electron in the case of sodium, becoming sodium cation, you have something that has a lot of biological importance. Chlorine, gaining an electron, becomes the chloride anion, and this, along with sodium ion, forms sodium chloride. But in our body, form electrolytes, and they help in nerve generation, nerve action potential generation. So it's very, very fascinating, and especially when you get to the higher chemistries. All right, moving on, non-metal versus non-metal. Remember the examples we gave above: glucose, C6H12O6, carbon dioxide, CO2, H2O, water. Okay, those are going to be non-metal with non-metal. This is sharing. Okay, sharing. So sharing electrons means double bonds, triple bonds, or even single bonds. All right, briefly, let's talk about a molecular formula versus empirical formula. The empirical formula is the lowest common denominator. The molecular formula is how the molecule actually is arranged. So the molecular formula and the empirical formula can be equal to one another. Okay, H2O, okay, 2 hydrogens, 1 oxygen cannot be reduced anymore. But C6H12O6 can be reduced. So what's the lowest common denominator? If I divide each of these numbers by 6, I get CH2O. So 6 divided by 6, 12 divided by 6, 6 divided by 6 gives me CH2O. That's the empirical formula for glucose. All right, the empirical formula for fructose is also going to be CH2O. All right, so a lot of molecules, a lot of sugars will have this empirical formula. You just increment times 2, times 3, times 4, and then here in this case times 6, you get glucose. Okay, the lowest common denominator for O3 and ozone, this is called ozone. Take this 3 divided by 3, you just get O. And then N2H4, this molecule is known as hydrazine. I don't expect you to know that. But take this 2 and the 4, what is the lowest common denominator? It's 2. Divide this 2 by 2, you get 1. Divide this 4 by 2, you get 2. So the empirical formula of hydrazine N2H4 is NH2. Right, ionic compounds. Okay, we have ionic compounds and we have covalent compounds. You should know the difference between the two. Ionic compounds are metal versus with a non-metal. And this is also known as ionic, as stated above. All right. So ionic compounds, shown in the blue, are really the elements that are going to form ionic compounds. And these are going to be +1. These group 2A is going to be +2. Halogens, group 7A -1. 6A are going to be -2. Nitrogen is going to be -3. You may want to memorize that. Aluminum is going to be +3. You may want to memorize that. How do we name these compounds? We name these compounds by doing what's known as switcheroo. All right, switcheroo. So this is how I teach naming ionic compounds and getting their formulas. So this is aluminum oxide, and it is composed of Al +3 and O -2. So you kind of have to reverse engineer this. So Al +3, the 3 goes to this, to O, and the -2 goes to Al. You get Al2O3. I think I have a video on nomenclature, so if you want to check that out, you'll get some practice of naming ionic compounds. Again, non-metals with metals. This is an electron exchange. This is an electron exchange. This is an electron switcheroo, quote unquote switcheroo. Calcium bromide, reverse engineer this. It's calcium +2. Br is -1. Switch them. The 2 goes here, and the minus goes to Ca, so that's calcium bromide. Let's do the switcheroo for sodium carbonate. Reverse engineer this. Na is Na+. CO3 -2 is the carbonate anion, carbonate ion, or carbonate anion. I hope you're learning your flashcards. I hope you're memorizing them. You should recognize this as the carbonate anion. Do the switcheroo. The plus goes to CO3 as a unit. The -2 goes to Na. So we have Na2CO3. Right? So again, review that YouTube video that's on Blackboard and also memorize your flashcards. Homework problems should help as well. Ionic compounds tend to be in an array, so they have this very lattice-like structure. Sodium chloride has a crystalline-like lattice structure because all the elements that compose that ionic compound are in a lattice. Right? You can see here, not so from covalent compounds. Okay, glucose is not in a lattice. Otherwise, we'd have a big problem if our body had crystalline glucose in the cells. That could be a very dangerous and detrimental to your health. So ionic compounds are lattice-like structures, and covalent compounds, carbon dioxide, glucose, water, non-metal plus non-metal are not going to be in this type of arrangement for the most part. By the way, if you take sodium chloride and dump it in water, you get sodium ion and chloride ion. So that's called solvation and hydration. The water actually causes the sodium chloride to dissociate into its component ions, and we'll talk about hydration and solvation later in the course. All right. Based on my experience, I see a lot of students miss this. Ionic compounds are referring to metals with a non-metal, and I'll even add here, you want to do the switcheroo for this. Switcheroo, right? Very important. Okay, switch the charges, and that will give you the chemical formula. All right, so hopefully you have your flashcards memorized. You can use your flashcards on the exam for expediency, but I am telling you, for the pre-meds, pre-physician assistant, anything in the medical field, STEM field, you're going to want to memorize this as quickly. You want this to become a language, so making chemistry easy means sort of embracing the language, and this is the language of chemistry. So expect you to memorize this or at least know it, and if you don't know it, make sure you have good flashcards for the exam. Alright, so naming ionic compounds. It's a metal with a non-metal. Notice the commonality here is IDE, I-D-E at the end. So barium chloride, potassium oxide, magnesium hydroxide, OH minus. Okay, know your flashcards. Potassium nitrate. Okay, here we don't have IDE, but we have ATE, the 8. Why is that? Okay, know your flashcards. NO3 minus is the nitrate polyatomic ion, so it's potassium nitrate. What happens if we have transition metals? Roman numerals. All right, so this is iron 2 chloride. This is iron 3 chloride. This is chromium 3 sulfide. Again, reverse engineer this. Iron is going to be plus 2. Cl will always be minus 1. Reverse engineer this. Iron is going to be plus 3. Cl is going to be minus 1. And reverse engineer this. Cr is going to be plus 3. It's a transition metal. S is going to be minus 2. The switcheroo gives you these chemical formulas. So you're going to have to reverse engineer this. And again, if you see anything in this transition metal rectangle, please, please, please put them as Roman numerals. All right, let's name some of these compounds. All right, this is going to be called copper 2 nitrate. All right, this compound is called potassium dihydrogen phosphate. Again, use your flashcard. This dihydrogen phosphate actually is an acid. It has that H. It has 2 H's and 2 protons. H plus is a proton, so it actually is an acid. And we'll talk about acid-base chemistry really in an incredible depth in chemistry too. What is this? NH4ClO3. So this is ammonium chloride. All right, NH4 is plus. Again, make sure you know your flashcards. And chlorate is ClO3 minus. So do the switcheroo with NH4 plus and ClO3 minus. The positive attracts to the minus, and the switcheroo makes it NH4ClO3, ammonium chloride. This is the ammonium ion, and this is the chlorate ion. This is the cation, this is the anion. This is an ionic compound. It is composed of a polyatomic ion and two polyatomic ions. NH4 plus is actually covalent. ClO3 minus is actually covalent. This has gained an electron, this has lost an electron. But this is a unit. This is a fundamental unit. All right, so this is ammonium chlorate, and the whole molecule, the whole compound is ionic. Mercury 1 nitrite, so this is Hg, and it's in the +1 situation. And nitrite is NO2 minus. So do the switcheroo on that, we get HgNO2. Cesium sulfide. Cesium is group 1, so as an ion it's going to be Cs +1. And sulfide, anyone know what sulfide is? Okay, it's S-2. Let's go back up here. Sulfide is S-2, just like oxide is O-2. And fluoride and iodide and all those other guys. S-2. Alright, we do the switcheroo, and what do we get? Do the switcheroo, we get CsS2. So that is the chemical formula for cesium sulfide. Calcium phosphate. Calcium is going to be +2. How do I know that? It's in group 2 of the periodic table. Phosphate. Alright, this really is a test to see who knows their flashcards. Phosphate is PO4-3. This is what we call a polyatomic anion. So PO4 has gained 3 electrons. This whole unit is covalent. Phosphorus and 4 oxygens, those are nonmetals, gain 3 electrons. So this whole thing is covalent. It has triple bonds, double bonds, whatever. But this entire phosphate is a polyatomic anion, reacts with the cation, which is +2. So the +2 reacts with the -3. It's an ionic compound. We'll do the switcheroo, and we're going to get Ca3PO4 2. Okay, and please, please, please put your subscripts and superscripts properly. So this is the chemical formula for calcium phosphate, and this is ionic. Even though the phosphate in and of itself is covalent, this whole unit, this whole molecule is ionic. Alright, silicon with chloride. Alright, so is this ionic or covalent? I don't think I mentioned this, but if you have 2 nonmetals, it's a covalent compound, but how do you name it? Alright, so you're going to name it utilizing prefixes. Silicon tetrachloride. It's covalent, use those prefixes. Well, we don't use mono per se. Di, tri, tetra, penta, hexa. How will you name this? P is a nonmetal, O is a nonmetal. Ask yourself the question, is this ionic or covalent? P is a nonmetal, O is a nonmetal. Ask yourself the question, is this ionic or covalent? Nonmetal with a nonmetal, it is covalent, so that's going to have some double bonds or some bonds, single, double, triple, it doesn't really matter. What matters is how we name this. 4 is tetra, so it's tetraphosphorus. What is the prefix for 10? It's deca. Deca oxide. So this is tetraphosphorus deca oxide. Carbon disulfide. Carbon is a nonmetal. Sulfide is S-2, but sulfide, which comes from sulfur, is a nonmetal. And carbon is a nonmetal. So just CS2. A nonmetal with the nonmetal prefixes. Disilicon hexabromide. Alright, di. It's 2, hexa is 6. Nonmetal with a nonmetal, it's a covalent compound. Alright, H3PO3. In our lab, you're going to deal with naming acids, but anytime you see an H as a leading element, that tells you that H can leave. And any substance that can give off H plus as a proton is an acid. So naming acids is different. It has its own set of rules. And you have a lab and an Excel spreadsheet where you'll name acids. This is phosphoric acid. Right? And again, that is nomenclature of acids, which is a separate sort of rule book. IO4 minus is the iodate ion. Right? Iodate ion. I don't know if this is in your flashcards or not, but this is the iodate ion. Alright, very important highlights here. Metal plus nonmetal is an ion, ionic compound. And if it's a transition metal, you're going to name it with a Roman numeral. Nonmetal plus nonmetal is going to use prefixes. Here's your carbon dioxide, here's your disilicon hexabromide, tetraphosphorus decaoxide. Nonmetal plus nonmetal, use those numeric prefixes. Metal plus metal, don't worry about it. We're not going to talk about it in this class. Alright, so an entire flowchart on how to name these. Alright, again, get your flashcards memorized. The quicker you appreciate chemistry has to do with the quicker you grasp the language. Those flashcards is the vernacular and language of chemistry. So knowing them will make you enjoy the course a little better. Unfortunately, the barrier to enjoying chemistry is memorizing those flashcards. Again, I'll let you use those flashcards for the exam. Alright, so make sure you go through this flowchart. Memorizing the flashcards is probably going to be key in understanding this flowchart. Alright, naming acids, a little bit tricky. First thing, let's define an acid. Acids give off protons, and protons for this course is going to be symbolized by H+. H+. Another name for H+ is proton. And the way we name these is a little bit different. We can name them by, it's just a different rule book. So the best way to learn it is just by examples. Dihydrogen phosphate, hydrogen phosphate, PO4 with the -3 charge. In your flashcards, that's the phosphate. When we add H's, we change the name. So perchloric acid actually comes from perchlorate. And so ClO4 minus is the perchlorate anion. And this just made me realize that I made a mistake. And that mistake is, I go all the way up, is that IO4 minus is the periodate ion. Okay, so IO4 minus is periodate. Bear with me as I go back down. ClO4 minus is perchlorate. ClO3 minus is chlorate. IO3 minus is iodate. Okay, BrO3 minus is bromate. Alright. Add an H, you get the chloric acid, or iodic acid, or bromic acid. ClO2 minus is chlorite. IO2 minus is iodite. BrO2 minus is bromite. Add an H plus, you get chlorous acid, bromous acid, iodous acid. And finally, these oxo acids, the least number of oxygens, 1 oxygen. Hypochlorite ion, ClO minus is hypochlorite. IO minus is iodite. BrO minus is bromite. All right. Add an H plus, you get hypochlorous acid. hyperiodous acid, hyperbromous acid, okay? Fluorine, FLO minus is hypofluorite, add an H plus, hypofluorous acid. Right? So like that, you can do oxo acids with the halogens. This works best with the halogens, group 7. All right, this flow chart gives you how to name oxo acids. There's another category called hydrates, and that's also going to be in your spreadsheet activity, your computer exercises that will comprise one of your labs. And hydrates basically require you to know the numeric prefixes, such as di, tri, tetra, penta, hexa, septa, octa. You'll get lots of practice with nomenclature in the computer exercise involving that Excel spreadsheet. For now, important points to realize: naming compounds, discriminating ionic compounds versus molecular compounds, covalent compounds. Ionic compounds, remember the switcheroo. Covalent compounds, remember the prefixes, the numeric prefixes. And naming acids, we just went through how to name some of these acids. Memorize your polyatomic anions, your polyatomic cations. So memorize the flashcards is basically what I'm telling you. And know how to calculate the number of protons, neutrons, and electrons in an element. All of this really is the best summary of Chapter 2.